Hello everyone. In the previous session, we studied about the common source amplifier without source resistance. So now in this session, we'll study the common source amplifier with a source resistance. This is the circuit configuration of this CS amplifier with source resistance. All the circuitry remains the same except for which here we have a source resistance that is connected at the source terminal. Okay, and here the input current to the MOSFET is 0 because the resistance here is very high, and so here we have coupling capacitor CC1 and CC2. They perform the same operation as they are performing in a common source amplifier without a source resistance. That is, they block the DC and allow only the AC signal. And here also this CS will act as a bypass capacitor, and it will protect the current source here. And this is the small signal equivalent circuit of the same. And here you can see that there is a T model here. Okay, T shape you can observe here, right? D and S, this line is perpendicular to this line here, gate. So this forms a T shape. Remember this. Okay, observe this carefully. During the explanation, you can get back to this and come to know more about it. And coming to the explanation, the RS is connected at the source lead. This is the first point that you're supposed to write, and the corresponding small signal model also we saw just now. And I told you that the transistor is being replaced by a T equivalent model. So instead of transistor here, I'm writing this T equivalent model. Okay, this is the current source that carries a current I. Previously it was GM into VGS. Here it is I, and it's the resistance of value 1 by GM. And apart from this, the drain resistance here RD, RL, and RG, and R signal, and V signal. It is all the same. And here I is equal to V by R, isn't it? So V is nothing but VI here. Okay, VI divided by 1 plus GM plus RS, because these two are in series. And in this configuration, the drain current that is flowing here is equal to the current I that is flowing here. Okay, and then so Rn is equal to Ri, that is equal to Rg, and Vi is equal to V signal into Rg divided by R signal plus Rg. So name this as equation 1. You will need it in future simplification and evaluation steps or whatever. So name this as equation 1. And VGS is equal to, VGS is here. Okay, this is equal to VI into 1 by GM divided by 1 by GM plus RS. See here, this VGS is equal to VI, okay, into the resistance across it is 1 by GM divided by 1 by GM plus RS. Okay, so I've written this here, and upon simplification, we will get VI divided by 1 plus GM into RS. So the VGS is the input voltage, isn't it? So is equal to VI divided by 1 plus GM into RS. So here we are connecting RS, okay, the source resistance, to the common source amplifier. So this source resistance, you can see it is in the denominator of this equation VGS. So this RS will have a control over this VGS magnitude. So it will see to it that this VGS will not become too large such that it brings nonlinear distortions into the circuitry. Okay, so this is the first benefit of using the source resistance. And next, one more benefit is that Using RS will help us to extend the useful bandwidth of the amplifier, and this is one more advantage. And it also acts as a negative feedback. This is the third advantage. Over all these advantages, we have one disadvantage, that is the voltage gain will be reduced. And the current ID, I mentioned this earlier, the current ID is equal to the current I flowing in the source lead. So this current ID that is flowing here is in the drain in the drain lead is equal to the current I that is flowing in the source lead. So I, we came to know that it is equal to VI divided by 1 by Gm plus Rs. So ID will also be equal to the same. Okay, and then uh, yeah, so upon simplification of this Vi by 1 by Gm plus Rs, so we'll get Gm into Vi divided by 1 plus Gm to Rs. So now thus including Rs, see here Rs is in the denominator, isn't it? So by including Rs, we are including Rs in this configuration of common source amplifier, isn't it? So by including Rs, this drain current is reduced by a factor of 1 plus Gm into Rs. Previously it was Gm into Vi. Now it is 1 plus Gm into Rs. Drain current is reduced, and the output voltage is equal to V naught. The output voltage V naught is equal to I into R, isn't it? What is I? I is I naught, and R is parallel combination of RD and RL. So V naught is equal to output current is nothing but the drain current. So since it is in the opposite direction, so minus ID into parallel combination of RD and RL. So what is ID equal to? Gm into Vi by 1 plus Gm into Rs, isn't it? So substitute this value here and we'll get V naught is equal to so much. Okay, and the voltage gain AV is equal to V naught by V in, isn't it? V in is nothing but Vi. So V naught we have found it out here. So substitute that, and V in is Vi. So this Vi and the one in the numerator of the equation of V naught will get cancelled, and we'll get AV, that is the voltage gain, is equal to minus Gm into RD parallel R naught by 1 plus Gm into Rs. So name this equation as 2. Now we need to calculate overall voltage gain. So overall voltage gain, open circuit voltage gain. Open circuit voltage gain meaning this RL is infinity, meaning it is not present at all. So this AV naught, so now we'll remove this RL. So now AV naught is equal to minus GM into RD, remove this RL, by 1 plus Gm into Rs. So it is just equal to minus GMRD by 1 plus Gm into Rs. I'll tell you how easily you can write the equation of AV naught from AV. Here you should remove this RL that is there in the equation of voltage gain in order to get open circuit voltage gain. That's all. It is as simple as that. And next, overall voltage gain, that is from VSIG to RL. That is from V signal to RL. Go back to this circuitry from this end to this end. Overall circuit gain. Sorry, voltage gain. So that is equal to GV. That is equal to V naught by V6. V naught we know here. We have calculated. Substitute the same equation. And then here I told you to remember equation 1, isn't it? Go back to it. And we have V signal is equal to equation 1. Vi is equal to V signal into Rg by Rg plus Rc, isn't it? So from this equation, note down what is V signal equal to. V signal is equal to Vi into Rg plus Rc divided by Rg. Okay. Substitute that here. Okay. And then simplify. See here, GM into RD parallel BI 1 plus this goes to the RG and this here. The numerator has VI here in VSIC, and in the numerator of V0 also we have VI, so they both will get cancelled. Okay, and this will be multiplied by the reciprocal of this, it goes up, so it will be minus Rg by Rg plus Rc into Gm into Rd parallel R divided by 1 plus Gm into Rs. So name this as equation 4. This is overall voltage gain. So now let's observe the voltage gain, the open circuit voltage gain, and the overall voltage gain. So all these have 1 plus Gm into Rs, 1 plus Gm into Rs, 1 plus Gm into Rs in the denominator. Whereas in analysis of common source amplifier without source resistance, we didn't have this. So here, what conclusion we draw from this study is that the voltage gain, the open circuit voltage gain, and the overall voltage gain GV is reduced by a factor of 1 plus Gm into Rs due to the addition of the source resistance. Therefore, this source resistance is also called as source degeneration resistance. So this is about the common source amplifier with source resistance. Solving one problem from common source amplifier without source resistance and with source resistance will suffice for the preparation of your examination. Okay, so don't worry much about it. I've solved the problem in the notes. Just go through it. It is just substitution and calculation of the values, so it is very easy. You can go through it. Okay, in the next session we'll continue with the second